So I'm not sure if I still need an introduction after all this, but my name's Priva H, I'm in 10th grade, and I had the real pleasure of working with Dr. Mindy Levine, who, fun fact, is Dr. Black's sister. So Dr. Levine graduated from Columbia University and did her postdoctoral fellowship in MIT. She currently teaches in the University of Rhode Island, and I believe is the director of the chemistry department. Now my project focused on new detection methods for detecting alcohols within a given solution, primarily looking at what type of alcohol is within the solution as opposed to whether or not there is an alcohol. What I mean by that is last year we worked on a project that detects whether or not there is an alcohol in the solution. My current project for this year worked on what type of alcohol is within the solution. We worked with color changing methods using the nonpolar and polar qualities of the molecules to create these results. So the reason we actually came up with this project in the first place is because, in general, these types of procedures and these types of techniques do not currently exist. So this would be the first at-home style detection method for an alcohol in the world, which is exciting. So our system looked specifically at the alcohols that are created by bacterial molecules. So bacteria such as E. coli, salmonella actually create alcohol when they're hosted in certain materials, such as pork. Now, these bacteria are very harmful and affect people all around the world, all day, every day. And they actually cause quite hundreds of deaths around the world yearly. So the alcohol detection is actually a new way to detect these bacteria before they are actually within someone's body. So these bacteria, such as salmonella, E. coli, can be found while they're within the food, as opposed to after they have infected someone. So the system, as I said before, relies on the polar and nonpolar qualities of the molecules that we use. So alcohol is a molecule that has a nonpolar section as well as a large polar section. So this is very important when we're working with cyclodextrin, which is a ring molecule, sugar ring, which is very, very nonpolar. So as we know, water is polar, so when you put the cyclodextrin within the water molecules, they form a sort of tunnel shape. I actually have pictures that I'll show later of this cyclodextrin. So when you would add alcohol to these molecules, alcohol, the nonpolar section of the alcohol, will be trying to move away from the water. Because the nonpolar section of the alcohol, water is polar, the alcohol wants to move as far away from the polar water. Therefore, it's going to embed itself within the cyclodextrin ring. So the alcohol is trying to move away and will embed itself within the cyclodextrin ring. Now, how do we use this to detect alcohols? So we use a lot of different techniques in order to find the solution, but what we use is a nonpolar, highly colored dye. So originally last year we worked with one dye specifically. This year we worked with two dyes. We used sanguine and Bo-Dippy dye. Now these dyes, we tested quite a few dyes, and these dyes were actually quite interesting because they react with each other. So as opposed to just each dye interacting with the alcohol on its own basis, these dyes, when they combine, turn very, very highlighter yellow. I kid you not, it looks radioactive. So we have this sanguine, which is dark blue, and we have the Bo-Dippy, which is kind of palish yellow, and together they turn highlighter yellow. So what happens is that the alcohol will move within the cyclodextrin. So the alcohol is sitting inside the cyclodextrin. When you add this nonpolar dye to the entire solution, the nonpolar dye, the Bo-Dippy specifically, will try to kick the alcohol out of the cyclodextrin. So this causes a color change, not only because of the actual external environment surrounding the alcohol molecule and surrounding the entire solution, but primarily because the Bo-Dippy dye is now going to interact with the sanguine, which is outside of the cyclodextrin. The reason this happens is because the Bo-Dippy is much more attracted to the inside of the cyclodextrin than the sanguine. So when the Bo-Dippy is kicked out, it'll interact with the sanguine, and it will actually create a chemical reaction turning bright yellow. So the original color will be more of a bluish kind of color, and after adding the alcohol, it will become more of a highlighter yellow, bright color. So this is, as I stated before, this is the Bo-Dippy, this is the sanguine, squaring, excuse me, I was saying sanguine, but that's a different dye we use. So these molecules are going to interact with the cyclodextrin. So we use different types of cyclodextrin to see which cyclodextrin would actually work the best. So alpha cyclodextrin has an interesting shape. It's more closed up at the end. The beta cyclodextrin is a bit bigger. The gamma is even bigger than that. So what happens is that we try this with the Bo-Dippy because that's the molecule that's primarily going within the cyclodextrin. So we tested them out to see what it would look like on this simulation that Dr. Levine got for us. It was very exciting. So we were able to test it out. So as opposed to having to try it out each time with another molecule each time, we were able to just simulate it on the computer, which worked very well. So these are my highlighters. It's very exciting because it was very, very bright. It was very exciting to show the neon colors, but I can't, so we'll deal with this. So it actually worked quite well. And so this graph specifically shows detecting whether or not there's an alcohol within the solution. So again, it's not such a great coloring. But if you compare it to the actual just with water in the solution, there's a very significant difference whether there's an alcohol or not. So first of all, you're able to detect whether or not there is an alcohol within the solution. Next, you want to look to see what type of alcohol is within the solution. So this we also got working very well. Unfortunately, this actually uses an algorithm that we haven't developed yet, but we have the data in order to develop this. So that was not what we were focusing on. We were looking on whether or not we could make the different alcohols interact differently with the solution as a whole. So here we're going to compare the different analytes. So the analytes are actually the alcohols themselves. So what is going to be give you the most significant change in the values of the alcohol? So we made a nice little photo booth and took pictures of this to detect the color of the solutions as a whole. So really the blue value and the hue saturation luminescence was the best way to detect what type of alcohol is in it. You can't see here, but each alcohol used very different values to convey its color. So specifically, you could see the ethyl alcohol. You could see the ethyl alcohol has a very, very, very low blue value as opposed to the other alcohols. So using the blue value, you're able to detect whether or not it is ethyl alcohol within the solution. So using these values, you're able to detect what type of alcohol as opposed to just if there is an alcohol in the solution. Now here we're comparing the analyte with cyclodextrin as opposed to without cyclodextrin, just to see if the cyclodextrin actually made a difference. The answer is yes, it did make a difference. So in conclusion, this was a very successful project, and it can be used, not currently, but it can be used if we create an algorithm, not only to detect whether or not there is an alcohol within the solution, but also what type of alcohol is within the solution. Before I conclude, I really have to give a very, very big shout out to Dr. Levine, because not only was she with me every step of the way, it was very, very hard to get these materials, because I did this in my garage. Just technically not allowed, but don't tell anyone. So she was able to secure us a grant. It worked out very well, and I really have her to thank. So thank you for listening.